This is the course Stochastic Process, and in this we are starting Module 3, that is Stationary and Autorecursive Process. This is a lecture 1 on the stationary process, and I will be talking the autorecursive process in the lecture 2. In this talk I am going to cover the introduction of the stationary process and a few definitions and the properties of the stationary process. Then there is a two important stationary processes. One is the stick sense stationary process, the second one is the wide sense stationary process. After this I am going to give few simple examples of a stationary process. Introduction. A stationary process is a stochastic process whose probabilistic laws remain unchanged through shift in times or in space. Stationarity is a key concept in the time series analysis, as it allows powerful techniques for modeling and forecasting to be developed. What is the meaning of time series? Time series is a set of data ordered in time, usually recorded at regular time interval. In probability theory, a time series, if you make out a time series is a collection of random variable indexed by time. Time series is a special case of stochastic processes. One of the main features of time series is the interdependency of observation over time. This interdependency needs to be accounted in the time series data modeling to improve temporal behavior and forecast of future movement. So, basically the stationary is used as a tool in time series analysis when the raw data are often transformed to become stationary. That means if you collect the raw data and that raw data need not be satisfying the times, it need not satisfy the stationary property, but using the stationarity property, the time series of that raw data is transformed so that you can model as well as you can forecast for the future movement by using the stationarity property. There are different forms of stationarity depending on which of the statistical properties of the time series are restricted. The most widely used form of stationarity are stick sense stationarity and weak sense stationarity. So, basically before we go to the two important types of stationary property, that is a weak sense stationary property and stick sense stationarity property, we will just see few definitions followed by these two important stationarity property. The first one is the mean function. Mean function is defined as the with the notation m of t, that is nothing but expectation of the random variable x of t. So, here the stochastic process is the collection of a random variable x of t over the t belonging to capital T, and you are defining the mean function as the function of t, that is expectation of random variable x of t. Sometimes this is going to be a function of t, sometimes it is going to be a independent of t. According to the function of a t or independent of t, we can classify the stochastic process later. So, this definition is going to be very important, that is mean function. The second one, it is a second order stochastic process. When we say a stochastic process is going to be a second order stochastic process if it satisfies the condition the second order moment is going to be finite for all t. If this condition is satisfied, that means if a random variables with the finite second order moment, then that corresponding stochastic process is called a second order stochastic process. That means there is a possibility the stochastic process may not satisfy the second order moment, may be infinite or it won't exist. In that case, it is not going to be called it as a second order process. So, whenever you collect the random variables, form a stochastic process and satisfying the second order moments are going to be finite for all t, then we say that stochastic process is going to be a second order process. The third definition is a covariance function. How to define the covariance function? Covariance function in notation, it is a C of s comma t, that is nothing but covariance of two random variables x s comma x t. Since it is a collection of random variable, so for each t you will have one random variable. So, that means you have here you have taken two s and t and you got the corresponding random variable and you are finding the covariance of these two random variables. That is nothing but the expectation of x of s, x of t minus expectation of x of s and the expectation of x of t. Obviously, since you are finding the covariance of any two random variable, obviously this stochastic process must be a second order stochastic process, so that the second order moments exist and you are able to find out the covariance of this one. That means the existence of the second order moments is going to be finite, that is assumed to be, that is assumed, and therefore you are getting the covariance of these two random variables. So, using that you are defining C of s comma t, that is a covariance. Since it is nothing, it is expectation of the product minus expectation of the individual one, it is going to satisfy, it satisfies the first condition. The C of s comma t is same as C of t comma s for all t comma s belonging to capital T, where capital T is the parameter space. From the parameter space, if you take any two t and s, then if you find out the covariance function of s comma t is same as a t comma s. The second property, using Schwarz inequality, you can always able to say the upper bound is going to be C of s comma s and C of t comma t. This is going to be exist because the second order moments are finite. Therefore, C of s comma s, that is nothing but the variance of x of s, and this is going to be the variance of x of t, and therefore, this is nothing but the product of the variance and the square root. So, this is going to be a finite quantity. Therefore, this has the upper bound of C of s comma t has the upper bound, the square root of product of variance of x of s and x of t. The third property, it is the covariance matrix. Non-negative definite also. That means for A1, A2, AN, that is a set of all, as a set of real numbers, and if you take TIs belonging to capital T, and if you find this double summation of j running from 1 to n and k running from 1 to n, aj and ak, these are all the real numbers with the covariance functions of tj comma tk. That double summation is nothing but the expectation of summation of aj's x of tj's whole square. This expectation quantity is always going to be greater than or equal to 0. Since it is a whole square, so the expectation of whole square quantity is always greater than or equal to 0 for all the set of all real numbers a1, a2, an, and the ti's are belonging to e, and this is nothing but the expectation of this quantity, and that quantity is always going to be greater than or equal to 0. So you can conclude the covariance function is going to be a non-negative definite. The fourth property, the sum as well as the product of any two covariance functions also covariance functions. The sum and the products also going to be the covariance function. This property needs elaboration. However, we assume these for this course. So, this four properties going to be used later whenever you would like to cross check whether the covariance function is going to be satisfied or how to find out the covariance function. So, these properties will be used. Now, we are moving into the fourth definition, that is autocorrelation. Autocorrelation function. The way we have defined the covariance function, now we are defining the autocorrelation function. It is defined with the notation r of s comma t, that is nothing but, or we can write it in the terms of expectation of x of t x of s minus expectation of x of t into expectation of x of s divided by the square root of variance of x of t and the square root of variance of x of s. So, the numerator can be written covariance of x of t comma s divided by square root of variance of x of t square root of variance of x of s. So, this is going to be used in with the notation r of s comma t, and this is going to be autocorrelation function for the random variable x of t and x of s. So, it basically describes the correlation between values of process at the different time points s and t. Sometimes we assume r of s comma t depends only on absolute of t minus s. In the later case, when we are discussing the stationary process, it is going to be depends only on the interval length, not the actual time. Therefore, the r of s comma t is going to be depend only on the length of the t minus s in absolute, not the actual s and t. Therefore, by assuming r of s comma t is going to be a only depends on t minus s, we can have r of, instead of two variables, I can use the one variable as the r of tau, that is nothing but the expectation of x of t minus mu multiplied by x of t plus tau minus mu, the expectation of that product, divided by sigma square. So, here I have made the one more assumption, the m of t, that is nothing but the expectation of x of t, that is going to be mu, and the variance of x of t is going to be sigma square. With that assumption only, the r of tau is going to be expectation of this product divided by sigma square, where the variance of x of t is going to be not a function of t, it is a constant, that is sigma square, and similarly the mean function expectation of x of t is going to be mu, that is also independent of t. Therefore, I can simplify this r of s comma t, the product expectation minus individual expectation, that can be simplified as expectation of this product, and so basically this is evaluated at x of t at x of t plus tau, and that difference is going to be tau. And this is also going to be a even function, that means it has r of tau is same as r of minus tau. And this autocorrelation function is used in time series analysis as well as signal processing. In the signal processing, we assume that the signal, the corresponding time series is satisfying the stationary property. Therefore, the stationarity property implies the autocorrelation function is going to be depends only on the length of the interval, not the actual time. Therefore, this r of tau will be used in the signal processing as well as in general time series analysis also. The fifth definition, so we are covering the different definitions which we want. The fifth definition, first we started with the mean function, second we started with the second order stochastic process, then third we have given the covariance function, and the fourth we have given the autocorrelation function. Now we are giving the fifth definition, that is independent increments. If for every t1 less than t2 less than tn, the random variables x of t2 minus x of t1 comma x of t3 minus x of t2 so on till x of tn minus x of tn minus 1 are mutually independent random variables for all n, then we say the corresponding stochastic process is having independent increment property. So, whenever you take a few t's, t1, t2, tn, and the increments, that is x of t2 minus x of t1 like that till x of tn minus x tn minus 1. So, these are all going to be the increment, and each one is a random variable. Therefore, the increment is also going to be a random variable, and you have a n such random variables, and suppose these n random variables are mutually independent random variable for all n. So, this is fixed for 1 n, like that if you go for all n, if this property is satisfied, then we can conclude the corresponding stochastic process having the property of independent increments. So, the independent increment that does not imply some other properties, but here what we are saying is the increments satisfies the mutually independent property. That means, if you find out the CDF of the joint CDF of this random variable, that is same as the product of the individual CDF. If that is property satisfied by all the n, then you can conclude that stochastic process has the independent increment. The next property or the next definition is ergodic property. What is the meaning of ergodic property? It says the time average of a function along a realization or sample exists almost everywhere and is related to the space average. What it means? Whenever the system or the stochastic process is ergodic, the time average is the same for all almost initial points. That is, the process evolves for a longer time, forgets its initial state. So, statistical sampling can be performed at one instant across a group of identical processes or sampled over time on a single process with no change in the measured result. We will discuss the ergodic property for the Markov process in detail later, but this ergodic property is going to be very important when you study the Markov property or when you study the stationarity property. Therefore, this ergodic properties always goes along with the stationarity property or goes along with the Markov property. Therefore, the stochastic property is going to behave in a different way, and that we are going to discuss later. The most important stationary process, that is a stick sense stationary process. First, let me start with the stick sense stationary process of order n, then I will define the stick sense stationary process for all order n, or there is a stick sense stationary process itself. If for arbitrary T1, T2 and so on Tn, the joint distribution of the random vector, that is x of T1, x of T2 and so on x of Tn, and the another random vector, that is x of T1 plus h, x of T2 plus h and so on x of Tn plus h, are the same for all h which is greater than 0, then we say the stochastic process is a stick sense stationary of order n, because here we restricted with the n random variable. So, we take n random variable taken at the points T1, T2 and Tn and find out the joint distribution of x of T1, x of T2 and x of Tn So, you can find out what is a joint distribution of this n random variable. Also, you find the joint distribution of n random variable shifted by h. That means earlier the random variable x of t1, now you have a random variable x of t1 plus h. With the same shift h, you do it with the t2. Therefore, the random variable x of t2 plus h. Similarly, the nth random variable is x of tn earlier. Now, you have a random variable x of tn plus h. So, you have another random vector with n random variables, and find out the joint distribution of that. If the joint distribution of this first n random variable as well as the joint distribution of the shifted by h, that random variable, if both the distributions are same, that means they are identically distributed, the joint distributions are going to be identical, then you can conclude this stochastic process is a Sticksen's stochastic process of order n, because you use the n random variable. If this is going to be satisfied, the other property is going to be satisfied for all n, then you can conclude the stochastic process is going to be a Sticksen's stationary process for any integer n. This is going to be a Sticksen's stationary process for any integer n. So, we start to cross checking the joint distribution of n random variable. So, if it is satisfying by only with the maximum some integer, then it is going to be a Sticksen's stationary process of order that n. If it is going to be satisfied for all n, then for any integer n, then it is going to be called it as a just Sticksen's stationary process. The next definition is a wide sense the next one is a wide sense or weakly stationary, or is another word covariance stationary process. When we say the given stochastic process is going to be a wide sense or weakly stationary or covariance stationary, if it is going to satisfy the following properties, following conditions: mean function, that is m of t, is independent of t. The second condition, the second order moment is going to be finite. Basically, the stochastic process is going to be a second order, moments are going to be finite. Third condition, if you find the covariance function c of s comma t, that is a function only on the time difference t minus s for all t comma s. If you find the covariance function for any two random variables x of s and x of t, then that is always going to be a function of the only the difference t minus s, not the actual t or actual s. That is, in words, in mathematically, you can write c of s comma t, that is going to be a function of t minus s in absolute. If this three property is going to be satisfied by any stochastic process, then we say that stochastic process is going to be a wide sense or weakly stationary or covariance stationary. This is entirely different from the Stickson stationary. The Stickson stationary, you are finding the joint distribution of n random variables, then find the joint distribution of n random variables shifted by h, and for all h greater than 0 and for all n, if that property is satisfied, then we say that is a Stickson stationary process. Whereas here we check the mean function is going to be independent of t, and the second order moment is going to be a finite value, and the covariance function is going to be a function of only the difference of t minus s. Therefore, any stochastic process satisfying the Stickson stationary process, Stickson stationary property, that does not imply the wide sense stationary property, as well as the wide sense stationary process need not be satisfied all the Stickson's property. Therefore, you cannot imply one stationary process that does not imply the wide sense, and the wide sense stationary process that does not imply the Stickson's stationary process. So, in the Stickson's process, what we are saying is it is a stochastic process whose joint distribution does not change when shift in time or space. As a result, the parameters such as the mean and variance, if they exist, also do not change over the time or position for the Stickson's stationary process. Now, I am going to give few examples for the stationary process. Maybe it could be a Stickson stationary process, or it could be a wide sense stationary process. The first example, let xi is going to be a IID random variables, independent identically distributed random variable, and assume that each one is going to be Bernoulli distributed random variable with the parameter p. In notation, it is a binomial distribution with the parameters 1 and p, that is same as each xi's are Bernoulli distributed random variables with the parameter p. Now, I am creating a stochastic process with those such IID random variable in which each random variable is a Bernoulli distributed random variable. Therefore, this is going to be a stochastic process. Now, you can verify whether it is going to be a Stickson's stationary process or a wide sense stationary process. The assumption is all the random variables are mutually independent, and each random variable is identically distributed, which is Bernoulli distributed. So, this is just for example sake we have taken, and if you find out the mean function for each random variable, that is going to be expectation of xi, and that is going to be the mean of Bernoulli distribution is going to be p, which is independent of I. The second condition, if you find out what is the second order moment of the second order moment is going to be 1 square into p and 0 into 1 minus p. So, therefore, that is also going to be p. So, if you find out c of some I comma j, instead of s comma t, you have I comma j, that is nothing but expectation of x of I, x of j minus expectation of x of I, expectation of x of j. If you find out this quantity, this is nothing but xi and xj, and since they are independent random variable, therefore expectation of xi into xj is nothing but the expectation of xi into expectation of xj, and that is same as this one. Therefore this is going to be 0 for all I is not equal to j. For I is equal to j, that is nothing but expectation of xi square minus expectation of xi whole square, that is nothing but the variance, and the variance of the random variable Bernoulli distribution, that is going to be npq. Therefore that is going to be p into 1 minus p for I is equal to j. And this values is independent of this values is going to be a function of I minus j, you can make out. Therefore since these all three properties of the weakly stationary property or wide sense stationary property is satisfied, therefore this is going to be a wide sense stationary process. In fact, even if the random variables are simply IADs, then too we can check that the process is wide sense stationary. For illustration purpose, we have discussed Bernoulli process. More examples on continuous time stochastic processes are discussed in the problem sheet. Now we can cross check whether this is going to be a stick sense stationary process also. If you find out the joint distribution of suppose you take few random variables x of I1, x of I2, x of I3, x of IN. So this is the n such random variable, and each random variables are Bernoulli distributed with the parameter p, and all are independent. Therefore the joint distribution is going to be the product of individual distribution. And if you shift this I1 with some number h, and x of I2 plus h, and x of I3 plus h, and so on, x of IN plus h, you shift those random variable with the h. If you find out the joint distribution, and since each one is a independent random variable, therefore the joint distribution by shifted by h, that is also going to be the product of those n random variables product. Therefore the distributions are again going to be identical, because each random variable is identical as well as mutually independent. Therefore the joint distribution is going to be product, and all are going to be identical. Therefore it is going to be power n of the distribution. So this is going to be satisfy the stick sense property, that is the joint distribution of this random variable and joint distribution of this random variable are going to be same for all h as well as for all n also. Since it is satisfied for all h greater than 0 and for all any integer n, therefore this is going to be the same collection of random variables. The stochastic process is going to be a stick sense stationary process. So this is the cooked up example in which this stochastic process is going to be a stick sense stationary process as well as a wide sense stationary process. But there are many situations in which stochastic process may be a stick sense, not a wide sense, and some stochastic process may be a wide sense stationary process, not the stick sense stationary process. And how this particular stochastic process become a stick sense and a wide sense, because of each random variable is mutually independent as well as identical. Therefore it is going to be a stick sense stationary process as well as the wide sense stationary process. I will have another example. in which it is going to be a only the it won't be a stick sense itself. Let me start with the example in which this stochastic process is a stick sense stationary process. The given xt is a stick sense stationary process with finite second order moment. So, you do not want the finite second order moment for the stick sense stationary process, but I have taken as example the given xt is going to be a stick sense stationary process along with the finite second order moment. Now, I am going to define the another stochastic process with the random variable y of t, that is a plus bt plus x of t. So, this is going to be a stochastic process. This is a stochastic process yt. Now, we want to check whether the yt is going to be a stationary stick sense stationary process or not. As well as whether this is going to be a wide sense stationary or not. The xt is a stick sense stationary process. Suppose you find out the mean for this random variable, the mean for this random variable, if you find out the mean for the y of t, where a and b are constant, therefore, this is going to be a function of t. Since a and b are constant, the mean of y of t is a function of t, therefore, this is a function of t. Since it is not satisfying the first property of the first condition to become a wide sense stationary process, therefore, the y of t is not a wide sense stationary process. We started with the stick sense stationary process and we created a new stochastic process y of t, that is a plus bt of xt plus xt, where a and b are constant. Now, if you find out the mean of y of t, mean function, that is going to be a function of t, that is nothing but that depends on t. Therefore, yt is not going to be a wide sense stationary process, whereas xt is a stick sense. Now, similarly, you can cross check whether the joint distribution of y of t and shifted by h, t is shifted by h, you can conclude this is also not going to be a, since it is a function of a t, since it is a, the mean is going to be a function of t and the y of t also involves the function of t as well as x of t. Even though x of t is a stick sense stationary process, the way you made a plus bt plus xt, you will end up the joint distributions are going to be different by the t with the shifted t plus h, it won't be satisfied. Therefore, you can conclude y of t is not a stick sense stationary process also. That means, from this example we can conclude whenever you have a stick sense stationary process, if you make a plus bt plus xt, definitely the y of t is not going to be a wide sense stationary process as well as a stick sense stationary process. We will go for the third example. In this third example, let me start with the stochastic process be a here this each random variables are uncorrelated random variables with the mean of each random variable is going to be some constant k, which may be assumed to be 0 in some situation. So, in general you keep the mean of each random variable is going to be some constant k, and you make x of m x of n, that is going to be its variance for m is equal to n, and for all other quantity you make it 0. Not only this, each random variables are uncorrelated random variable, that means if you find out the correlation coefficient, that is going to be 0, and the mean is going to be constant, and the expectation of the product of any two random variables, if they are different, it is 0, and obviously if they are same, since you make the assumption, therefore this is going to be a variance sigma square. If you cross check all the properties of all the conditions of the wide sense stationarity property, starting with the mean function, and second order moment exists, that is finite, and the covariance function of any two random variables is going to be a function of only the difference, that all those three conditions are going to be satisfied. Therefore, you can come to the conclusion, I am not working out here, this is going to be a weakly stationary process or wide sense stationary process, or it is going to be called it as a covariance stationary process also. And this stochastic process is also called a white noise process. This is very important in the signal processing. You keep the uncorrelated random variable with this assumption, the mean is going to be a constant, which may be 0, and the product of expectation is going to be these values, and this is going to be a weakly stationary process, in the sense it satisfies all three conditions of that weak sense or wide sense stationary process, and this stochastic process is called a white noise process. Note that this stochastic process, we did not make the distribution of each random variable xn. What is the distribution of xn is not defined here. Without that, we give all the assumptions of the mean and variance. Therefore, this is going to be very useful in the time series analysis as well as the signal processing, and this particular stochastic process is called the white noise. And sometimes we make the assumption the xn's are going to be normally distributed random variable also, but in general we won't define, we won't give what is the assumption, what is the distribution of xn. Without that, this stochastic process is going to be called it as a white noise process. Addition to the wide sense stationary process, one can assume that ergodic property also satisfied along with wide sense stationary property For illustration purpose, we have discussed Bernoulli process. That means the given stochastic process is a wide sense stationary process, as well as it is the ergodic properties also satisfied. In that case, the mean function is going to be a sum independent of t, that you can make it as the mu, and auto covariance function is going to be a r of tau only, because it is a Whiteson stationary process. Therefore, the mean is independent of t, and the autocorrelation function is going to be a function with the only tau, and we have a ergodic property. Therefore, you can find the mean can be estimated from the time average. So, this is possible only if the ergodic property is satisfied. So, the mean can be estimated with the up arrow, that means the estimation of a mean, that is same as 1 divided by 2 times t and minus t to t of x of t dt. So, this is possible as long as the stochastic process is so in general I define t belonging to capital T, that t is different from this t. So, here you have the time interval of the length 2t. Within the 2t, if you find out the time average, and that time average quantity is going to be the estimation for the mean. That means, if mu t converges in the squared mean to mu as t tends to infinity, then the process is going to be a mean ergodic. That stochastic process is going to be called it as a mean ergodic process. Similarly, one can estimate other higher order moments also, provided the process is ergodic with respect to those moments. So, here I have made the ergodic with respect to the mean. Therefore, you are estimating the mean with the ergodic property. Similarly, if the given stochastic process is satisfying the ergodic property with the higher order moment, then those measures also can be estimated in the same way. So, here the mu t converges in in squared mean to mu as a t tends to infinity. So, that is the conclusion we are getting from the ergodic property along with the Whiteson stationary property. With this, let me stop the today's lecture, and some more examples for the stationary process. So, maybe those example may be a Whiteson stationary process or Stickson stationary process that I am going to give in the next lecture. So, in the today's lecture, what I have covered is what is a stationary process, and to conclude, or for a given stochastic process is going to be a stationary process. For that, we have given few definitions. So, with those definitions, we can come to the conclusion the given stochastic process is going to be a Whiteson stationary process or Stickson stationary process. And I have given 3 examples in today's lecture, and I will give 2 more examples of a stationary process in the next lecture. Then I will go for some simple stationary process, that is autoregressive process and moving average process, and some more stochastic process for the stationary process example. I will give it in the lecture 2. With this, the today's lecture is over.